Yeah, okay. Good morning, and thank you very much to Prof. Zai, who is willing to give a guest lecture to us. And I hope that this is actually a continuation of a quite long and fruitful collaboration between ITS and SIT, which I think started around in 2018, where we have a world class professor and we have a GPBL, Global Project-Based Learning, which is still going until now, and actually started from last year. Professor Gu Zai is the adjunct professor of ITS, which is proposed by the mathematics department, and we hope that this collaboration will be continue further and can be beneficial to all of us. Okay, so in this opportunity, Prof. Zai will share his knowledge in a lecture about Lyapunov Stability Theory in modern control systems. Yeah, so to all students, if I think if you have any questions, feel free to ask Prof. Zai. I think he will be very happy to discuss with you, especially in the area of systems and control theory. And if you have maybe some difficulty to ask your questions, you can also ask in Indonesian, and we will try to communicate it in English, I think. Okay, so the lecture in our university usually around 100 minutes. So yeah, so to be the same, I think it's better to have around 100 minutes for the lecture. Yeah, so you can do it a little bit more, that's fine. Okay, I think that's it. Do you have anything to say, Pak Subhan, or shall we immediately start?
Okay, I just would like to say thank you so much, Prof. Zai.
Thank you. It's my pleasure.
Yeah. We have a very fruitful cooperation with SIT, and currently Prof. Zai is the head of the department as well at SIT, Prof. Zai. Yeah, I think that's what I would like to say. Thank you so much again, Prof. Zai. Hopefully we can see soon face to face, not via online, Prof. Zai.
Yeah, sure. Yeah.
Because we have a very good cooperation. We have Helisa as well as you and the supervisor for her doctoral as well, and many things. Again, thank you so much, Prof. Zai.
Okay, thank you.
I give it back to Master Diki. Thank you.
Okay, thank you very much, Pak Subhan. Yeah, okay, Prof. Zai, feel free to start whenever you are comfortable. Okay, thank you.
Okay, thank you very much. First of all, I would like to thank Dr. Subhan, Dr. Diki, and maybe I have to say Dr. Helisia. It's a doctor candidate, and and maybe I have several other lectures I don't know very well, but I would like to thank you guys very much to attend this guest lecture. As mentioned by Dr. Subhan and Dr. Diki, I had the pleasure to work together with many lecturers in Department of Mathematics of ITS, and of course I'm very happy to keep the collaboration between my department, myself, and the lecturers. And of course, I would like to welcome the interested students who would like to work together with me or with some other lecturers. Actually, that's the main reason I would like to give my lecture here, because I want more and more students will be interested in control theory, which is it's a very interesting topic for me, and And okay, so let me start my my lecture. And because the time is about 100 minutes, so I don't want to take the question at the finally because maybe you may forget the content. So I will ask for questions sometimes, maybe after 10 minutes, after 20 minutes. So then I will keep going. Okay, so if you have any question, you can write in the chat window, or you can just shout out. So no problem for me. Okay. Okay, so let me share my PowerPoint with you. Okay. So can you see my PowerPoint? No problem.
Yes, we can see it.
Okay. Okay. Good. Good. Okay. So the topic is Lyapunov Stability Theory in modern control systems. So you can see there are two keywords in the topic. First, is modern control systems. So we are talking about control systems, and especially in the modern control system area. And then we'll talk about the Lyapunov Stability Theory, which is a very interesting and very fundamental theory in control theory. So okay, so the outline of my talk today can be divided into three parts. I mean, basically two parts. The first one, as I mentioned right now, I would like maybe most of you are familiar with control systems, but I would like to mention a little more about modern control systems, so that in the future, if you want to consider some topic in your undergraduate thesis or master thesis, or even in PhD thesis, you can record some interesting topic in control theory. And then I will talk about Lyapunov stability, and I will mention a little more about how to design Lyapunov functions when we talk about Lyapunov stability. So this is the main the outline of my talk today. Okay, so I will use about 20 minutes to talk about modern control systems. Okay. So modern control systems. Well, this is a slide I used in many situations to talk about what a control is. Okay, so I think most of you are in Department of Mathematics. So what is the relation between control and mathematics, and maybe control and optimization? There are a lot of things we can do actually in real systems. So this is a situation about control. Okay, so suppose you are driving your car here. Your car is here, and it is a slope. Okay, so it is not a flat road. It's just a slope. And you before your car, there's another car. Okay, and also there is a limitation of velocity of car's velocity. It's about 50 kilometers per hour. Okay. So when you drive your car, okay, you have to take care, right? You have to think about a lot of things. First of all, you have to keep the speed limitation, right? Then you have to take care your car don't get crashed, with the car before you, right? So in this case, okay, actually there are many control issues. Okay, it may be speed control. You have to adjust your car's velocity so that, for example, it is less than 50 kilometers per hour, right? And okay, you use your eyes to watch the car before you. Then you have to adjust your car's velocity. And actually here, I use distance, not only speed but also distance, right? You have to keep a safe distance between your car and the car before you, right? So, and then what do we use? Okay, when driving a car, we use accelerator and brake. When we want to increase the speed, we use accelerator, right? When we want to decrease the speed to stop the car, we use our brakes. So you know, here in this situation, actually we are doing control. We are thinking about how to control our car. You know, I mean, it is a kind of online approach. Not only for 1 second, for 5 minutes. You have to do it, you know, every minute, right? So it is a kind of control by using your eyes to censor the distance between your car and another car, and you have to use your hand to deal with your handle, and you have to use your feet to use the accelerator and the brake. Right? So you know, actually this is the very real situation we use control frequently in our everyday life. So so I would like to introduce you a very typical diagram to describe feedback control I mean, this is not only in modern control systems, but also in any control systems, right? So here we have a process. So process maybe we may use a car, we may use a robot, we may use a satellite, or many different things here. So process here, it is the object we would like to think about, or we may use system sometimes. So for a real system, okay, there may be distance, there may be disturbance, right? So I would like to use some comment here. So our car is here, right? So the actual output may be the car's position, or maybe the car's velocity. And then our, okay, for example, reference input. So it may be, you know, it may be the distance between your car and the car before you, or it may be the desired car velocity, say 50 kilometers per hour. So then we take a kind of adjustment. You know, we compute the difference between the desired reference input and the real output. And then actually this is we need to think more in our theory how to design the controller to adjust the actuator. Actuator in our car system actually is the accelerator or the brake, right? So, well, I mean, in real system, of course, there may be a lot of disturbance, you know, and the most disturbance cannot be measured very clearly. And as I mentioned, we need to use our eye to measure the actual output, maybe the car's velocity, maybe the distance. Okay. So as you can see in this diagram, we have a lot of things to deal with a real system. Okay. If you are okay, if you okay, let me erase. If you are interested in the theory, you can think about how to design a controller. If you are interested in measurement, you may think about how to design your sensor to measure the real output. And if you are interested in experiments, you may think about how to design the actuator to deliver the real input to the process. And of course, okay, and if you are interested in the data process, then we also have a research area which is called system identification. Actually, Dr. Subhan is an expert in this area. So we also need to use a lot of data to describe the system, to know a little more about the real system. So this is a typical feedback control system when you want to think about the the whole image of a control system and many other research issues. Okay, so let me stop here, and I would like to move forward. Okay, so I would like to use very quickly several examples to describe how to describe a dynamical system. In modern control system area. So the first example is a very simple mechanical system. It is composed of three basic mechanical elements: mass, spring, and damper. So I think you guys have seen this figure in many textbooks, right? We have a card here whose the mass m here, and we have a spring here, and we have a damper here. And then, suppose if there's no force adding to the card, then it will stay there, right? If we add some force, for example, pull the card to the right, then of course the card will begin to move to the right, right? So we use a function y of t to describe the moving distance from the original position. Then, I think you know how to describe this mechanical system, right? It is very easy. It is very easy because the force f of t now can works for into three parts, right? So let me show you the dynamic equation. It is very easy, right? So the first one is about the acceleration of the card, and the second one is a kind of resistance by the damper, and the third part is corresponding to the resistance by the spring. So this MDK system, a very simple mechanical system, can be described by a second order differential equation, right? And of course, because this is a mechanical system, M, D, K are all positive numbers, positive scalars, right? So this is this is a motion system. This is a motion system. Then of course here we our purpose is to let me erase the remarks here. Okay, so our purpose is to consider how to design the force, right? Maybe maybe the card is not in the original position, so we need to design the force f of t so that the card is in the original. Will return to the original position, or may stay in some desired position, or maybe want to adjust the car's velocity. Okay, so there are many different purposes for this mechanical system. Okay, so as I wrote here, here the control input for this system is f of t. It's the force. And then our control purpose maybe maybe we want to. I'm sorry. Okay, no problem. Okay, so adjust the position of the mass, or maybe want to adjust the velocity of the mass, which means we may want to consider the moving distance of the car, or we want to consider the velocity of the car. So there are many different ideas about the system. So which means we want to choose our control input so that some desired performance of the system would have. Okay. So this is about the control input, control output, or and the control performance. So then, what do we do in our modern control system? Okay, let me move to the next one. Okay, actually in modern control systems, we would like to change this system into a first order derivative, because this is a second order differential equation, right? So then, okay, what do we do? Okay, because we have a second order derivative here, we need to do something to this system. Okay, we define x1 to be yt, and okay, we define another variable x2 as the derivative, the first derivative of yt. Then, of course, there's a relation between x1 and x2, because x1 is yt and x2 is y dot. It's the first order derivative, right? So then we have the relation between x1 and x2, which means, okay, so let me show you the result here. So then we have the result x1 dot equal x2. And by using x1, x2, we can change the original one into a first order differential equation. But of course, now we have two variables, right? We have x1 and x2 here. So which means we change the original second order differential equations into two first order differential equations, right? So well, this is actually the form we would like to use in modern control systems. And then we would like to summarize this system, okay? Because we have two differential equations, we use, let me use one. We use vector and matrices, okay, here. So we define a vector composed of x1, x2. It is a column vector. Then we can summarize the two differential equations by using a matrix and another matrix before. I mean, here we just separate the x part and the u part. And of course, we want to consider y here. So then we can write yt by using the new defined x vector. So which is actually here, so y, because y is equal to x1. So if we want to use the vector, then we need to another vector before the x vector. So so then, okay, then let me erase then actually this is the so-called state space representation or state space equation in modern control systems. The first one, we have the state equation, which is actually a family of first order linear equations. And the second one is called output equation, which describes the relation between the x vector and our output. And then here x is called state variable or state vector, and A, B, C are called system matrix. So A is a system matrix, and B is an input matrix, and C is called an output matrix. So this is the state space representation for the first example, the first mechanical system. Okay, I think all students have no problem, have no difficulty in these equations, right? No problem, right? Do you guys have any question about the first example? No problem, right? I think maybe you have learned about this example in your control course, right? No problem, right?
Yes, I think they have already know about.
Okay, good. Just to a very quick review about control systems. Okay, so let's move to a second example. This is also a very well-known example. It is about electric circuit, which is composed of three basic elements here. So I think all of you know here, right? we have a resistor here, we have a coil here, we have a condenser here. So then, okay, if the voltage here, we can adjust the voltage here. Then, okay, suppose we would like to adjust, okay, the voltage on the condenser here. So then, okay, how to describe this this system or this control problem by using the modern control theory? Okay, it is also quite easy. Okay, if we write the voltage equation for this single circuit, you know, it's very easy, right? Because you know the voltage VI is here. It is composed. I mean, it is divided into three parts. Okay, the resistor part, the coil part, and the condenser part. Oh, I'm sorry. This is the L part. This is C part. No. I'm sorry. So I think most of you have no difficulty understanding this equation. But now, okay, compared with the mechanical system, we have only first order differential derivative. But now we have a new term, which is a kind of integral term. So it is not, you know, I mean, maybe this is not so easy for some of you. So in control theory, in modern control, we also want to change this term into first order derivative. Okay. So well, I will talk about this on next page. But then, okay, I would like to talk about the control input. Okay, so here the control input. Okay, is here. Maybe of course, you know, I have talked about the control input is the VI here. We can. This is something we can add to the system. And for example, we want to adjust the voltage on C. So here, VO is something we want to adjust here. Then, okay, so this is also a control system. We would like to design the voltage V sub I to obtain the desired voltage on C, maybe. So this is also a control problem. Then let me move to the next page. Okay, it's also related to how to change this differential integral system, integral equation into first order derivatives, right? So, well, I think you also you have learned about it. Okay, so because we have this integral term. Okay, we would like to define this term by using a new variable x sub 2. And the original IT here, we use x1 here. Okay. So then, of course, you know there's a relation between x1 and x2, right? Because x1 is IT, x2 is a kind of integral of IT, I tau, right? So then, okay, considering this kind of relation, we can write down the system, the first order differential equation. So as you can see here, x2 dot equals 1 over c x1, right? You know, if you consider a derivative of x2, then you can obtain the second equation. Okay, and the first one actually goes to the first line, the first differential equation, right? So then while yt is the voltage on C, which means yt is here, which means yt equals x2, right? So then yt is here. We need a row vector 0, 1 multiplied by the x vector, so that this is equal to x2. Okay. So then, you know, we can obtain the same form as in the mechanical system, right? So so let me summarize this guys. Okay. Well, so then we have the same form, right? The same state equation, which is composed of the system matrix part and the control part. And the output equation, we also use the same C to describe the relation between X and Y. And of course, we XT is also the same form. It's the same ABC, but of course the matrices value are different from the mechanical system. I would like to say this is a general form. In a modern control system, we call it a state space representation. And actually, in some systems, we also have some another term, d plus dut in the output. When there is a relation, there is a direct relation between the input and the output. In some system, we also have these guys. So in that case, we usually, if you read a paper, then some paper may see we have ABCD, we have the ABCD here to describe the whole system. Although here I didn't use capital BCD because U and X, U and Y are scalars. But if we use capital ABCD, which means maybe the vector UT and YT are not scalars. So then we use capital BCD here. Okay, so this is the state space representation. And actually, this is a linear system in modern control theory. Okay, and I would like to emphasize for linear system. Okay, it's very clear to separate an AXT and BUT. And actually, I will give you another example. Mechanical system in many cases, it may be difficult to write into a matrix multiplied by X. And in some case, maybe it's difficult to separate XT from UT. They may be coupled. Okay. So, is there any question? Oh, no question. It's not question. No problem. Okay. So,
I have a question, Prof. Zai.
Sure.
Yeah. Could you go back to the previous slide?
Sure.
Yeah, this one. I was wondering when you have x2 equals 1 divided by c, the integral of 0 until t, and then something in tau. Did you use the second fundamental theorem of calculus to obtain the derivative, or it's something different?
Second what?
Did you use the second fundamental theorem of calculus to obtain the derivative of this integral form?
Yes.
Oh,
yes. Actually, that's it. That's it. Okay. So if some of you are not familiar with the derivative of x2, then of course we have a t here because the t is here. So this is an integral. Then if you consider the derivative, then of course you will have 1 over c and I of t. Okay. Well, of course we suppose I of 0 is 0 here. Okay. So then it is here, which means this is the relation between x2 and x1. Okay.
Thank you very much.
Okay. Thank you for your question. Do you guys have any other question? No problem, right? Very easy, right? Okay. So because these two examples are linear systems, it may be very easy for you guys to understand. Okay. So now let me move to a little more complicated case. Okay. So we have done this. Okay. So this is also a very typical example in many papers, in many textbooks. It is also a mechanical system. I call it an inverted pendulum on a card. So here we have a card here, and the mass is capital M here, and it can move on the surface. Okay, And because we have inverted pendulum on the card, so this is the pendulum here. So and of course it can rotate here, right? This is a mechanical system because we have a mass, we have a card here, we have a pendulum here, and let me erase the because the pendulum can, of course, it may be here, it may be here, it can rotate. So there's an angle here. I use theta of t to describe the angle between the pendulum and the vertical position. Okay, so actually in this kind of system, we usually our control purpose is want the pendulum to keep this kind of position. Okay, to keep the vertical position. Why is this problem important? Because it has a lot of application in real world. For example, if we want to use a big cart to let me see, to move a very big robot, or maybe a very big satellite here. Of course, the car go ahead, right? Then if the robot, or if the satellite, or if the rocket fell down, then it may be maybe broke. So that's the reason we want to use the force. It's a kind of horizontal force to add to the cart, so that the position of the pendulum can keep a kind of desirable angle. Okay, so this is a very well-known example in many control textbooks. So okay, so now of course we need to use some model to describe this system, right? Okay, then let me erase the remarks here. So then actually, okay, well, there are many different ways to obtain the dynamic equation for this system. And well, I think you can check many references to obtain this kind of equations. Okay, this is about the horizontal dynamics about for both the cart and the pendulum. And the first one is about mainly about the rotation equation for the pendulum. So as you can see, okay, this is compared with the first two examples, these two equations are much more complicated, right? Why? Because we have first we have x. X is the position change of the cart, the displacement of the cart, and the theta is the angle of the pendulum. And we have okay, second order derivative for both x and y and x and theta. Of course, we have first order, but we have a kind of a square, and moreover we have sine theta, cosine theta, and we have the product between cosine theta and theta dot dot. So it is quite complicated. I mean, if you have a chance to see this kind of papers, then they may first emphasize this is quite a difficult system to deal with. Actually, it is not easy. And so then what do we do in modern control theory? Okay, so before that, as I mentioned right now, let me suppose we would like to choose our control input. So our control input is f of t. Is so it's here. It's the force added to the cart. And suppose we would like to adjust the angle of the pendulum. So which means, okay, yt is equal to theta t, right? If you want to adjust the velocity, the angular velocity of the pendulum, then yt must be set to the first derivative of theta t, right? So it depends on how you your control per objective for the system. So let me move to the next page. Okay, in this case, what do we have? Okay, because we have second order derivative, so we can first solve the second order x dot dot and theta dot dot by using the first order and the theta and x. So then, okay, in modern control theory, we need to do a little more for these two equations. Because we want to use first order derivative to describe the dynamics of the system. So we use what? We use x1 equal theta and x2 equal theta dot, which means, of course, x1 equals x2 equals x1 dot. And we suppose x3 equals x, then x4 equals x dot, which means x4 equals x3 dot, right? So then, okay, of course, we can use these definitions to rewrite the first two second order derivative equations. We can obtain this kind of first order differential equations. These two equations describe the relation between all the variables. And the first one goes to what? Goes to the second one. And the second one goes to the final one. Well, this is only a representation. It it doesn't decrease the difficulty of the system, because if you take a look at the right side of the differential equations, again, we have this kind of sine x1 and x1 dot square and cos x1, and we also have cos x1 square. It is quite difficult to deal with. Okay, but of course, we call this kind of representation because we have sine and a square. So this is a nonlinear control system. Okay, and we'll talk about a little more about nonlinear system from now. Before that, I would like to emphasize here. So this is now for nonlinear system, because the right side, it is not a linear term. So the general form for the state space description or representation now becomes this kind of form. It can be described by just a vector f. Okay, but now x of t, it is not a linear term, and u, it is also here. We only know there are two variables, maybe vector variables, variable vectors. So we use a general form, f of x of t, u of t, and even if in the present example we can write yt in a linear form, but the general output equation for nonlinear system is you may say it can be described by another nonlinear function g. So this is the general state space representation for nonlinear systems. And of course, here now we have four variables. X of t is also a column vector, a 4x1 vector, composed of x sub 1, x sub 2, x sub 3, and x sub 4. It is called a state variable vector, or simply state vector here. So this is the example for nonlinear systems. Okay, and well, I think this is maybe the first part of my lecture. Just to give you some basic knowledge about modern control theory. basically, we need to change the original dynamic equation. It may be a motion equation. It may be a voltage balance equation. It may be some other equation. And it may be high order differential equation. It may be a kind of differential integral equation. But in modern control theory, we need to define some new variables to change the original equation into a family of first order differential equations. Okay. Okay, so I would like to take some question. If you guys have any question, you may ask right now. No question? Maybe just give you a chance to review what you have learned in control courses, right? No problem, right? Okay, good. This is what I imagine. I think most of you are very smart. So basically, no problem, for the state space representation. So now maybe I would like to move to the second part of my talk, which is the main topic. Okay, so the Lyapunov Stability Theory. Okay, well, maybe I don't have to mention who is Lyapunov, right? Lyapunov is a Russian. Actually, he's a Russian mathematician. He of course he made a lot of contribution, not only in mathematics but also in engineering. So of course, now thanks to him, we have a lot of research topic by using the so-called Lyapunov theory here. Okay. So well, let me first use the linear systems to give you some idea about why we need the Lyapunov function. Okay, so for this kind of linear system, x dot equal axt, which means in our state space representation, ut equals 0, which means the case without control. Okay, right? So well, I will show you a picture. In many systems, okay, the control is already in the system, or there may be we don't need to control the system. Okay, so for this kind of system, okay, so how we define the stability? Okay, we say this system is stable, or more exactly, we say the system is asymptotically stable if and only if for any initial value x of t will converge to 0. Okay, so here if you forget what you have learned in the control, so the key point is here: for whatever initial value x of t will converge to 0. But okay, actually in today's lecture, I don't use a very exact word to mention the solution region of the system. If you check the textbook, basically, maybe in many textbooks, they will use a kind of region to talk about the solution range of the system. Actually, for linear system, we can consider the whole state space. But for nonlinear system, usually many people use a kind of region to limit the possible range of the solution. But anyway, the key point is for any initial value x of t, if converge to 0, we say the system is asymptotically stable. Okay, so then if you say for linear system, actually, I think if you remember the linear system theory, we can compute, we can solve the system. Okay, by using a kind of a state transition matrix or function or matrix functional, right? So here, I use e to the power of at. So this is a transition matrix here, right? And well, of course, it is an extension of the exponential function. But of course, now here the power of is a matrix. It is not a scalar here. So well, if you are not familiar with this state transition matrix, you may need to check the control textbook. And well, actually, this state transition matrix, it is a kind of combination of what? Of exponential functions, e to the power lambda I of at. So here, lambda I of a is what? Is the eigenvalues of the system matrix A. Okay. So then, okay, because this is a combination of the exponential functions, and we need what? We need x of t converge to 0. Then you can tell very clearly, okay, for linear systems, x dot equal axt, the system is asymptotically stable if and only if what? All the real parts, here, the real parts of the eigenvalues of A are all negative, right? Because here, lambda I of A is the eigenvalue. Let me suppose, okay, for maybe in some case it may be -1, of course. Okay, e to the power minus t converges to 0, no problem, right? In other case, it may be minus, for example, -2 plus minus 3j, okay. Then it was no problem, right? E to the power of -2t, because in this case it corresponds to what? It corresponds to e to the power -2t multiplied by what? By some sine and cosine functions, right? No problem, right? And so which means, okay, in these examples, what is more important is what? Well, let me change my color here. It is the real parts, -1 and -2, which will dominate the convergence of the state variable x of t. So this is a very well-known fact. Okay, for real systems, the system is asymptotically stable if and only if the real parts of the eigenvalues of A are all negative. Very clear, For small system, for low order system, of course, we can compute the eigenvalue. We can tell from the eigenvalues whether a system is asymptotically stable or not, right? So in this sense, okay, we don't need a Lyapunov function for this kind of linear systems, because we can do a lot. We can compute the eigenvalue. It is very clear. It is a if and only if function, necessary and sufficient function, no problem. Well, actually, the Lyapunov function is important because it can deal with a lot of different systems in addition to this one. We start from this simple system, just want to get some clear image about the Lyapunov function. It is not only for this system; it's for more complicated system, for nonlinear system, for some other maybe linear, but may be different from this form. Okay, that's the reason I would like to start from this very easy system, but it will be extended to more complex systems. So okay, so now okay, I would like to talk how the Lyapunov function is related to this linear system. Okay, it's very simple, right? And how is it related to the Lyapunov function? Okay. So let me move to the next one. Okay. Okay. So because this is the same content as in the previous page. We know very clear this system is asymptotically stable if and only if. This is a definition, right? X of t converges to 0. Because now, please remember, remember x of t now is a vector. Okay, so this is the different thing. Okay, now x of t is a vector. It is composed of many elements. So here I use x sub 1, x sub 2, and x sub n, which means there are n elements in the state vector. So of course, I think you guys know very clearly, right? This means what? This means, okay, every xi of t must converge to 0, right? So of course, if you want, you can add an absolute value here, or no problem, because this is a scalar, no problem. So then, okay, we can think of a condition. If we don't want to use a scalar to describe the stability, then of course we can consider a kind of function to describe the convergence, right? This is also if and only if condition. If, okay, x1 square plus x2 square plus xn square. If this kind of value, okay, the limit is 0, converge to 0, then of course, any xi also need to converge to 0, which means the whole vector x of t also converge to 0, right? So this is also very clear, no problem. Okay, but there's a quite a big big difference between these two. The difference is here. The difference is, x of t here is a vector, but this guy now is a scalar function. Okay, xi is a scalar, x2 is a scalar, xn is a scalar function, so the whole y is a scalar function. Then we can use the very basic calculus to think about a lot of approach for the limit of this kind of scalar functions. This is a scalar function, much easier to deal with, right? Okay, so now let's move to the next page. Okay, because now remember, the asymptotic stability is reduced to, okay, we have two if and only if. This is if and only if. This is also if and only if. So which means the AS is equal to this linear function converge to 0. Okay. So now this scalar function, how to evaluate the limit of this function. This is scalar function, right? And because it is composed of x1 square plus x2 square. It is composed of n non-negative terms, right? xy square or xs square are non-negative, greater than or equal to 0, right? For non-negative position, if we want the convergence is 0, then if you record the basic calculus, then you may think you may figure out one way to deal with it, right? So actually, this is what we have on the next page. Okay, so wait a minute. Yeah. So how to check this limit for any initial value here? Here I use v sub 1 to denote this scalar function. This is one approach, right? Because v sub 1 is a non-negative function. If a non-negative function, if the derivative, okay, if the derivative is negative, which means v1 of x will decrease, right? For all time t. And okay, then because we have x1 square plus x2 square plus x2 square, the lower bound is 0. Then finally, it will reach 0, right? So this is the idea. This is the first idea about how to use a scalar function. Here, v1 x of t is composed of the the summation of all squared xi. Okay, so if we know, okay, the derivative of v1 is negative for non-zero x of t, then it is okay. Okay, so this is basically this is the idea behind the Lyapunov function, and we will define this kind of v1, a kind of Lyapunov function. Okay. Okay, so now, okay, this is one idea. Then, okay, now, but I would like to emphasize. This is not a necessary and sufficient condition. This is only a sufficient condition. Okay, if this is true, if this is true, we can obtain the first limit is 0, right? This is not a necessary and sufficient condition. I will tell you why. And actually, we have some example on the pages later. Okay. So anyway, we can use this kind of idea to evaluate whether the limit of v1 is 0 or not. So now let's go to next page. Okay. Oh, wait a minute. Okay. So it works well. I mean, it works well for some systems. Here is an example for the case. Well, v1 works very well for some systems. So if you have I mean, if you can use your MATLAB software, of course you can do the simulation very well for this kind of very simple system. Okay, it's a second order system, right? And the matrix A is also very, very simple. And of course you can compute the eigenvalue of this matrix. Okay, then okay, you write the phase portrait of this linear system. Okay, I think you guys know the meaning of phase portrait, right? Phase portrait means, okay, so so this is the x1 is the horizontal axis, and x2 is the vertical axis. So if the initial value is here, okay, it will converge to 0. So it's 0 here. If the initial value is here, it also converge to 0. If the initial value is here, it also converges 0. You can see all the arrows, goes toward the original here, right? So here, so this is 0 point. I mean, so you can, I mean, here, although the axis, the limit is 4 and 5, you can use a larger value to draw this picture to tell this system is is asymptotic stable, which means no matter where you start, the initial value start, the x of t will converge to 0. So now, okay, we know the system is stable by using this phase portrait. We can also use the eigenvalue of this matrix to tell the system is asymptotic stable. And now let's check whether this is work. This evaluation is good or not. Okay, so let's compute let's check this one. Okay, so how to check it? Because v1 here, now we have v1 equals v1 is the summation of all squares, right? So v1 here is x1 square plus x2 square, and we want to compute the derivative, right? So which means we have, for x1 square we have 2x1 and x1 dot. For x2 square we have 2x2 and x2 square. And then, okay, what is x1 dot, x2 dot? X1 dot, actually we need to write the first differential equation, right? which means what? X1 dot equals what? Minus 2 X1, is it right? And plus X2, is it correct?
Yeah.
So I think similarly you can write X2, okay, X2 dot. So this is actually we have here, okay. X1 dot is here, X2 dot corresponds to -1 and X3 here. So then, okay, no dot, right? We have all variables here. So then we can compute all the summation here. Then what do we have? Because you can see here 2 minus 2x1 x1 x2 and plus x1 x2 they cancel with each other. Then we have what? We have minus 4x1 square minus 6x2 square, which means, okay, for any non-zero x, okay, the derivative of v1 will be negative. Then of course, no matter if x is 0, then of course, v1 is 0, it will stay there. For any non-zero x, v1 will decrease, right? Then it will decrease until xt reach to 0. So this is actually, necessary and sufficient to the phase portrait here. Okay, right? Very clear, right? Do you guys have any question about this example? It is very simple, but it gives you the how to compute the derivative of the scalar function. Okay. Very interesting, right? So now, okay, so this is the case. This is the case. V1 works well for a very simple system. Okay. So now let me give you the case where V1 doesn't work very well. Okay. So let me give you the example here. This V1 doesn't work very well for many other systems, actually. So let me change the system matrix a little. I just changed what? I just changed the A matrix to another one here. It is also second order. A second order linear differential equations, right? Of course, if you compute the eigenvalue of this matrix, what are the eigenvalues of this matrix? It's very simple, right? What is it? The eigenvalue is what? It's -1 plus minus. I think you guys know very clearly, right? Square root of 1000j. Is it clear? Lambda plus 1, and plus 1000, right? So this is actually this is the eigenvalue of this matrix, which means what? Which means, okay, the real parts of the eigenvalues are -1, which means this system must be asymptotically stable, right? So then, okay, let's write the let's use only one trajectory. This is not the phase portrait. This is only one trajectory starting from what? From 10, 10. Okay, I think you can tell from the figure. So here we will start from here, and x1 is 10, and x2 is also 10. We start from 10. Okay, then okay, you start from here. It goes to this is arrow here, and it goes to the fourth quadrant and the third quadrant and the second quadrant, and then go back to the first quadrant. So now you can tell, okay, this system is asymptotically stable, and it will converge. I mean, although quite slow, it converges to 0. I mean, for although here I only give the trajectory from 10, 10. Even if you change the initial value, the system will converge to 0, no problem. But then, okay, so not only the eigenvalue, but also the state trajectory tell us this system is asymptotically stable. But then let's check whether this criteria, this inequality is true or not. Okay, so let's compute. Okay, Wait a minute. So again, we computed the derivative of V1. V1 is what? V1 is x1 squared plus x2 squared. So this is the same as as for the previous example. But now x1 dot, x2 dot is different, right? What is x1 dot? x1 dot is what? x1 is minus x1 plus 100 x2. Is that correct?
Yes.
And x2 dot is what? x2 is what? Minus 10x1 minus yx2, minus 1 minus x2. So let's do the computation. Okay. So then what do we have? Now now the cross term x1 x2 doesn't cancel each other. We have what? We have this kind of a final result for the derivative of v1 minus 2x1 squared minus 2x2 squared. These two are okay. They are negative. But this one, okay, 180 x1 x2, of course, this term is not always negative, right? Especially in the first quadrant, both x1 x2 are positive, then this term will be positive, right? So that's the reason. Okay, that's the reason. Actually, v1 v2 is a kind of the square of the norm, right? So we start from here. Actually, in the first quadrant. So this is 0. Where is 0? 0 is here. So the norm of the xt actually is increasing. Is it correct? So that's the reason. That's the reason why in this case v1 it doesn't work. It doesn't tell us whether the system is asymptotically stable or not. Because what? Because now the derivative of v1 is not negative for non-zero xft. And more precisely, it is positive in the first and the third quadrants. It is negative in the second and fourth quadrants. Okay. So now you can tell, okay, this v1 xt, we call it a Lyapunov function candidate, but it doesn't work for this nonlinear system. No, sorry, this linear system. Although it's quite clear from eigenvalue, from maybe from phase portrait or the state trajectory. Okay. But if we want to use linear Lyapunov function, a scalar function to evaluate the convergence of x, at least this kind of x1, which means x1 squared plus x2 squared, doesn't work. Okay, so then we need to think about how to change this v1 so that it works well for this system. Right? So this is our question. Okay, how to change v1 so that it works well for the present system. Okay. Okay, so actually in this case, it's quite easy. I give you guys 1 minute to think about. We only change one parameter, one number, one value, then it works well. Okay, so the hint is here. We want to change v1, v2. So we want to change, x1 squared plus x2 squared doesn't okay, right? Then what kind of value? If we use what other value, then it may work. So what kind of value should we change? Alicia, may I ask you the idea?
-1? No, Sensei.
-1?
But minus?
Here? No minus, because we need the the basic idea is we want a positive function to decrease until it reaches 0. Do you remember, we have trouble with the cross term, right? If we can manage to cancel this kind of cross term, then we're okay, right? So now we have 2x1 square 100, which means we have 200 x1 x2, but we only have -2 -20 x1 x2, right? No idea?
We need to.
If we change this guy to what?
10. No, Sensei.
Yeah, man, you're perfect. Man, yeah, well, that's it. Let's see, let me show you the answer. Actually, this is your answer, not my answer. So the answer by Felicia is actually given by the next page. Okay. If we change the second value, the coefficient before x2 square to 10, then things will be totally different. Okay, so the function, of course, are positive, no problem. But then, okay, if we compute the derivative, now we have 10. So then we have 20 x2 square, x2 dot. Then we compute we substitute x1 dot, x2 dot. Then, of course, we have what? We have 20 here, we have -10 here. We have 2 and 100 here. Then, plus and minus, they cancel with each other. Now we're happy because, 200 x1, x2, plus and minus, they cancel each other. We only have -2x1 square and -20 x2 square. Of course, both of them are negative for whatever, for whatever non-negative, for non-zero x, which means this kind of V2 works well for the second system. Okay, so I mean, because Felicia is very smart, so he can figure out this kind of Lyapunov function. I mean, I used quite a long time to think about this function. It's not easy. It's not easy. And actually, we will talk about how to obtain this kind of Lyapunov function even for linear systems. Okay. So anyway, for the present system, okay, we know it is asymptotically stable. We know the eigenvalue of the system matrix A, I mean, the real parts are all negative. Everything is okay. And we are also very happy we can find a Lyapunov function, I mean, a scalar function V2 here, so that the derivative of the function is also negative for non-zero x until it reaches 0. Okay, so we are happy. The final result is here. Okay, we can, because V2 is is a non-negative function, and it keeps decreasing for non-zero x, and finally it will converge to 0. Of course, x of t also converge of 0 for whatever initial value. So we're happy, right? Okay. So this is the just give you a kind of illustration for a scalar function. We want to use a scalar function to evaluate the convergence of the state vector x of t. Okay, and we used a very simple example to serve the kind of scalar function. Okay. Now, okay, I think I need to. Okay, do you guys have any question about these two examples? No problem, right? Very easy and very interesting. Is it all right? Okay, so, yeah, okay, thank you very much. So now let me erase my remarks here. Yeah, I'm happy. I just show you a happy face. It's my happy face. Okay, so now, okay, let me move to the general definition for now. Okay, we are, because in modern control, of course, we have both linear and nonlinear systems. Of course, we have this kind of linear system, okay, and nonlinear systems. If f of x is ax, then it's a linear system. Basically, for nonlinear system, okay, the right side is described by f of x. Because now we are interested in the definition, we just suppose the control is already there, or the case without control. Actually, in this case, it is called autonomous system, and we usually suppose f is Lipschitz continuous, so that the solution of the system is unique. Then actually, okay, for this kind of nonlinear system, okay, we need to define the equilibrium point of the system. Okay, so the definition here. Okay, given this system, okay, if the right side, okay, how to solve the equilibrium point? We solve the right side equals 0. If we find a solution xe, then this kind of xe is called an equilibrium point. Okay, so the meaning is very clear, right? Because you know, the right side equals 0, which means x star equals 0. Which means if x is xe, then it will stay there. It will not move. It will stay there forever, right? So that's the reason why we call it the equilibrium point. Of course, you know, if ax, if in the linear case, if fx equal ax, right? Then of course, ax equals 0, then at least we can obtain x equals 0 is one equilibrium point, right? Then I will show you actually not only for this kind of linear system, but also for a nonlinear system. In many systems, there are maybe more than 2 equilibrium points. Okay, but anyway, here I want to suppose. Let me erase the okay, what is here? Let me suppose what? Suppose 0 is one. Let me suppose 0 is one equilibrium point, which means here xe equals 0 is one equilibrium point. You may ask, why we can suppose xe equals 0? It is very easy. If xe is not 0, then we can use okay, x equal x minus xe. Then we just substitute x bar here into the original one. Then we can obtain for x bar. I mean the equilibrium point. Always we have a one equilibrium point 0. No problem. Okay. So that's the reason why we can suppose xe equals 0 is an equilibrium point for nonlinear system without losing generality. So now, okay, so now let's go to the definition here. Actually, for nonlinear system, we need, I mean, to define the stability a little more carefully. Okay, so we have 3 definitions for nonlinear systems. The first one is here. Okay, because you know, for nonlinear system, we may have more than 2 equilibrium points. We have to say the equilibrium point is stable. Sometimes we may omit this guy, but if we say correctly, we will say stable in the sense of Lyapunov if. Now this may be a little difficult for you guys to understand. Okay, so this is what for any positive epsilon, there exists a positive data, so that if the initial value is inside the delta ball, then the norm of xt will always be smaller than the epsilon for whatever. Then you may wonder, okay, oh, it's so difficult to understand. Now let me give you a figure. Okay, I think this figure is easier for you to understand. So what do we mean? Okay, given a epsilon here, okay, we suppose 0 is the equilibrium point. Given this epsilon, we can always find a delta here. If the initial value is inside the small ball, starting from here, then the state will always be inside the epsilon, the epsilon ball. Okay, so this is the meaning of the state of stable in the sense of Lyapunov. And actually, you can tell from this figure, okay, delta basically is less than epsilon or equal to epsilon. Okay, so now you can tell from this figure. Okay, the meaning of stable in the sense of Lyapunov means, okay, epsilon is a kind of a tolerable convergence for, it's not a point, it is a region. Given a tolerable region, epsilon, we can find a region for the initial value so that it doesn't diverge, it doesn't go out. It always stays in the region. Okay, so actually this is much more interesting for any real systems. In real systems, usually we the next concept is about asymptotic stable, but this is actually more practical because it gives us a practical tolerable region for the order state. So this is the first definition for stability. Then the next definition actually is the same as for linear system. Wait a minute. Oh, is my time okay? Maybe I need another 15 minutes.
It's fine. It's fine. It's
fine. Fine, no problem. Okay.
Fine.
Maybe some of you are hungry. No problem. Okay. Oh yeah. The time for you guys is okay. Actually, in the Japanese time now is 12:30. So. I'm not hungry. I'm okay. No problem. So now let me move to the next page. Okay. The next definition is about asymptotic stable. If they could, we say the system is asymptotic stable if it is stable. First, it is stable. And moreover, if we can find a small region so that x of t will converge to 0, then we say the system is asymptotic stable. Again, if we use the same figure, okay, in the previous figure, let me change my color here. It stops here. It stops inside the epsilon region. But now we need it to converge to 0, okay, which means what? It doesn't stop here. It has to go toward the 0. Finally, we need the x of t will converge to 0. So this is the difference between asymptotic stable and the stable in the sense of Lyapunov. And actually one more, let me tell you one more. We say the equilibrium point is exponentially stable if we can find some positive scalars so that the norm of xt is less than what? Less than the initial values norm multiplied by an exponential function with a minus lambda t. Lambda here is a positive number. Of course, e to the power of minus lambda t, of course, this function will converge to 0, right? Which means, okay, so here, although the delta ball is the same, it's the same here, but if this inequality holds, then we can always we can always obtain asymptotic stable, right? So which means what? Which means actually we can obtain the relation between these three concepts. Okay, if the system is exponentially stable, if this is true, then we can we have asymptotic stable. And because AS requires the system is stable, then of course we also need the original system is Lyapunov stable in the sense of Lyapunov. Okay, so this is the image of I mean the formal definition for Lyapunov stability and asymptotic stable or exponentially stable. Okay. Any question by now? I mean about the definition of Lyapunov function? No problem. Okay, great. Oh, I now we have 30 participants. I'm happy. We have maybe the participants increased. No problem. Okay, I'm happy. So now, okay, let me. I think you guys, if you check any textbook in control theory or even in differential equations, you can find this kind of definition. The formal definition about asymptotic stable, exponential stable, and the Lyapunov stable. Okay. So now let's go to the next page. Okay. Yeah, actually, this is a picture I use in my control course. What is it here? So this figure tells us three different concepts. Okay, so we have a surface. This is a surface. We have a surface here, and so here we have some friction, which means here this is the bottom of the surface. So we have some friction here, but no friction otherwhere. Then on this surface, we may have 4 equilibrium points. If we place the ball very, very carefully, I mean, if we sometimes we may place our ball here, it just stay there sometimes, right? No problem, right? Of course, for A and B, no problem. If we place our ball here, no problem. Then now just imagine the case. If we give some perturbation, some noise, some force to the ball, what will happen? Okay, for example, for the ball on for the ball A, if we push, okay, if we give some force here, push the ball to here, okay, then what will happen? It will go up because there's no friction. It will go down and go up here and go down here, up and down here. Because there's no friction, right? It will not stop, right? And how about B? B, if we do the same thing to the ball, okay, push the ball, put the ball here, then just leave it there, then it will go down, go up and go down. But because of the friction, finally, I mean, the height will decrease, and finally it will stop here, right? How about C1 and C2? C1 and C2. If we give the ball some force from the right, from the left, okay, then the ball, okay, for example, C1, it will go down. It will never return to the original position. The same thing is true for C2. Is that right? Okay, so actually this is, is related to the 3 concepts. Okay, the A ball is the stable in the sense of Lyapunov. And the C1 and C2 is the case of unstable. And the B ball, the ball B, okay, because of the friction, okay, we can tell the equilibrium points B is asymptotically stable. Okay, very interesting, right? So I mean, I think you can use all the same picture to tell people, oh, I can understand the difference between asymptotic stable and stable in the Lyapunov and unstable. Okay. So well, I'm sorry I used too much time here. Okay, so let me do a little quickly. So now actually I because of time I will give you the answer. Actually, I would like you guys to think about the trajectory of this system. This is a nonlinear system. X dot equals x multiplied by 1 minus x. Of course, the right side is, we have x squared here. This is a nonlinear system. And okay, how many equilibrium points does this system have? Do you remember how to compute the equilibrium points? Let the right side equal 0. Is that right? Is that correct? Then of course, clearly x equals 0, x equals 0, or x equal 1. We have 2 equilibrium points for these nonlinear systems. Then in this case, we need to say, okay, whether x equals 0 is stable, whether x equal 1 is stable, whether they are asymptotic stable or not, right? So my question here is, okay, I would like you to imagine what kind of trajectory the system will have for the initial value, 0.01, 0.5, 0.9, and 2.0. The reason why, the reason I choose, okay, the 4 initial value is, okay, 0.01 is close to x equals 0. 0.9 is close to x equal 1. And okay, well, 0.5, well, it's just in the middle of these 2 initial values, the equilibrium points. And okay, 2.0 is a little far from the second equilibrium points. What kind of trajectory do you think the system will have? Well, of course, if you can, I mean, actually, we can use the differential equation theory to solve this guy. You can obtain the solution, or of course, you can use MATLAB to do the simulation. No problem. Well, because I'm not good at mathematics, I use MATLAB to do the simulation for me. Okay, so let me give you my answer. Okay, the answer is here. This is the result in MATLAB. Very clear, very clear. This is not 0. This is the case. This is the case starting from 0.01 because it is too small. So it looks like 0, but it's not 0. So now you can see, okay, all the trajectories, okay, starting from the 4 initial points, they finally converge to 1. Okay, so now it's very interesting, right? Which tells us what? Which tells us xe equals 0 is a stable, is an equilibrium points, and actually it is asymptotically stable. Starting from here, starting from here, starting from here, starting from a lot of initial values, it will converge to 0, converting to 1. So starting from any initial value, of course, including the points close to 1, they will converge to 0, which tells us now in this case x equal 1 is an asymptotically stable point for this nonlinear system. How about x equals 0? we start from here, right? We start from here. If x equals 0 is a stable point, then Lyapunov stability tells us the state will not go out, will not go far, right? But now it goes far. It escaped from the 0 point, which means, okay, x equals 0 is an unstable equilibrium point in the present case. Okay, so well, I mean, of course, you can try some many other initial value. Okay, here, well, although I don't want to tell you the answer. If you try some minus value x equals x0 minus 1, you will find some strange phenomena. Then you can think what happened. Okay, so but well, I mean, I would like to stop here. I want to tell you in the present case, xe equal 1 is equilibrium point, which is asymptotically stable. So oh, how many pages do I have? Okay, I would do quickly actually. So this is the main theorem I would like to use to conclude. Maybe it's kind of conclusion. Okay, so by now, okay, I use v1x, v2x, and v3x, right? So to tell you, okay, for linear or a nonlinear system, if we can find a scalar function which is positive for non-zero x, okay, actually this is what this is called positive definite. For non-zero x, vx must be positive, and we can find, if we can find, okay, for all x, v dot is non-positive, which means okay, this v dot x is non-positive definite. Then we can tell, okay, vx is a positive function. It will not increase for any x, right? It will stay in some desired region, right? Then in that case, we can say xe, the equilibrium point, is stable in the sense of the Lyapunov function. Okay, if furthermore we can find that v dot is negative for non-zero x. Actually, this is called a negative definite. Then, okay, as in the case of a linear function, right, a linear system, right? Then we can tell vx will decrease for whatever non-zero x until the state reach 0. Then, of course, in that case, x will converge to 0. And then we say x equals 0 is asymptotically stable. Okay, so this is actually the main theorem, the Lyapunov theorem for stability, for asymptotic stability. Okay, and the final, my final, actually, I have several slides, but I would like to leave it to the next lecture. But I would like to use one example, because for linear system, it's quite easy to compute this kind of vx. Actually, for nonlinear system, how to seek this kind of function is a key point. It's a very important. So let me give you. Okay. Oh, actually, I have one definition. Oh, sorry. So this kind of vx is called a Lyapunov function if it is true, if it is satisfied the above function. I mean, the positive definite condition and the negative definite function. This is what we say is a Lyapunov function. Before we can confirm this condition, we usually say it is a Lyapunov function candidate. Okay. So how to find this kind of Lyapunov function candidate is very important, right? Now let me use an example. Well, this is a nonlinear system, right? Nonlinear because of what? Because we have two x2 square. We have x1, x2 here, right? So well, because we don't have time, I don't want to ask someone to give me his idea. So let me tell you. This is one idea. Okay, if we use this Lyapunov function candidate, we need to check whether it works well or not, right? Okay, then we do the same thing for the linear system. We compute the derivative with v3. Then we have this kind of one. Then what do we have? We have the same thing. We have almost the same idea. I mean, the same thing as before. Okay, 2x1, 2x2 square, and the 4x2 and the minus x1 square. These guys cancel with each other. Then we have what? We have minus 2x1 square minus 4x2 square, which means, okay, which actually this is equal to minus 2 v3. And of course, because v3 is a positive function, which means this guy is always negative for non-zero x, right? Which means, of course, you know, this guy, satisfies the condition in the Lyapunov stability theorem. We can tell, okay, the limit of v3 is 0. Then we can tell x of t will converge to 0 for whatever initial value. Okay, so actually, okay, so if we write down the phase portrait of this nonlinear system, we can obtain the figure here. Okay, wherever it starts. Okay, you may start from here, then finally converge 0. You may start from here, it will converge to 0. Of course, the same thing is here from 0, right? If you start from here, the same thing converge to 0. Okay, so which tells us actually this system is asymptotically stable, and actually it is true for whatever initial value in the two-dimensional x1, x2 plane. Okay. Okay, so well, I think it's time for me to conclude my talk. Actually, I have prepared some a little more. Maybe we can talk next time. Let me just give you what I prepared. I will not explain. So wait a minute. So I prepared a lot. Okay. Well, so so for linear case, how to solve it, how to use the Lyapunov matrix, and for nonlinear guys, then how to construct the Lyapunov function. Okay, so but I would leave it to the next lecture. Okay, so thank you guys. Okay, so if you guys have any question, I am happy to ask, happy to answer. Okay, thank you.
Thank you very much, Prof. Zai, for the lecture. I think it was very interesting for me.
Thank you.
Are there any questions from the students? Yeah, maybe where they are still thinking. I think the approach that you were presenting about first using Vx equals x1 square plus x2 square, and then trying to find the constants to eliminate the cross terms. It was the first time I saw such an approach, because
really?
in the book I usually see the Lyapunov equation, and then we have to P or something like that. This is
yeah, that
for me. Yeah.
That is true for linear system. It is okay, but of course for nonlinear system we cannot do that, right?
Yeah.
So that's my idea. I mean, in my next lecture I will talk a little more how to design this kind of Lyapunov function. Okay.
Yeah, but yeah, thank you. Are there any questions from the students? Oh yeah.
Yeah, I have one question.
Yeah, there is a question. So
Yeah, I have one question in the chart. Okay, the question is always a Lyapunov function of a linear combination of x1 squared? Very good question, man. Yeah, it's well, I mean the answer is no. The answer is no. Well, actually, for this system, you know, for example, you know, maybe for this system, you know, we need to check. We check it a little more, but I suppose you try this kind of one. For example, you may try bx1 square, ax1 square, and bx2. For example, we want the function be positive. That's the reason why we use square. But of course, you can use the even order of the state variable. For example, you can even consider this kind of guys. Then okay, of course, a and b must be positive, right? Then you can you do the same thing to compute the derivative of v3. Then you may design your a and b so that the final derivative is negative for non-zero x. It is possible to obtain some different Lyapunov functions. Okay, so well, of course, here I don't want to use time to compute, but I think you can try it for this system or for some other system. So then the answer is okay. The summation of variable squares is only one candidate. Of course, especially for nonlinear system, we can use some different. Actually, let me show you. Not in today's topic, but for example, for this nonlinear system, right? So then we have this kind of Lyapunov function candidate. Now you see what we have a similar term as before, but now we have this kind of term. You know, even you know we can even use sine, cosine, this kind of function to construct our Lyapunov function. Okay. So is my answer okay for you? I mean.
Yeah, thank you. It's okay for me.
It's okay. Okay, thank you very much.
Pak Zahab is one of the lecturer in our department, and he is now studying a doctoral degree in United Arab Emirates, I think. Is it true, Pak Zahab?
Can I ask one more question?
Yeah, sure.
Yeah. You are a doctor student. Okay, great.
When we want to find the Lyapunov functions, do we always try to find the exact functions, or can we try solve it numerically?
Well, of course, you know, if we try numerical solution, because you know, we can get some image. We can get some image about the trajectory convergence. But okay, because you know our definition for stability is what? Is for whatever initial value. You remember? So which means what? Which means where is it? So here, you know, whatever initial value, we want to know whether the norm is bounded or whether xt will converge to 0 or not, right? So if we only do the numerical simulation, we of course, you know, x sub 0, the initial value is they are not limited, right? That we have infinite number of x0. We cannot confirm infinite number of x0. That's the reason why we need some efficient function to tell us whether the answer is true for any initial value. Okay, so that's my answer. Is that okay for you?
Okay, thank you, Professor.
Okay, thank you.
Are there any other questions? Pak Sahab, are there any other additional questions?
No, Mr. Ricky, no.
Yeah. So, yeah, I was surprised when about the last example that you give, h dot equals what?
Yes, interesting, right?
The last one.
Yeah, I know. This guy, right?
No. The polynomial one, the non-linear polynomial. No, not this. The polynomial. Yeah, this one. Yeah.
This one? Yeah.
But at first, I thought this because this is a nonlinear systems and it is square and multiplication x1 x2. I thought the Lyapunov function must be very complicated, but it turns out that it's quite simple. I was
yes.
That such
Well, of course, yeah, of course. This is example. I can arrange. I can arrange the actually. These guys are linear terms, no problem. But these terms, is something. If I don't know this answer, it is also difficult for me. So, well, because this is example, I have this Lyapunov function, then I consider some term here. So it's just an example. It is okay. But well, without this guy, if I'm given this example, or even the scalar is different, then it may be different for me. So yeah, the same.
Yeah. Okay. Yeah, I think that's it. Maybe for today's lecture. Oh yeah, there is a student asking whether you will share the slides. Is it okay if you share the slides?
Okay. I will send you the PDF. Is that okay?
Yes, it's okay. Maybe they wanted to look at the equations more carefully later.
Oh, I see. Okay. I will check the PowerPoint and make a PDF file for you and send you. Okay.
You can send the PDF file to me later. It's not hurry, so it's fine. Whenever
okay.
comfortable.
Great.
Yeah. Okay. I think that's it for today's lecture. And we thank you very much to Prof. Zai for giving such an interesting lecture. And it was, I think, interesting, easy to follow. And although it's maybe for many people it looks difficult, but I think almost all of us can follow. And yeah, as mentioned by Prof. Zai, we hope that in the future there will be the continuation, if possible, Prof. Zai, maybe in the next semester. Hopefully, there will be the next part of this lecture. Yeah. Okay. Thank you very much, Prof. Zai, for the lecture, and also for the students. If there are, we apologize if there are some inconvenience during the lecture, and we apologize for delaying your lunch. Thank you very much.
Oh, thank you very much. Thank you, Dr. Diki. And thank you, Khirisia. Thank you, Dr. Subahan. Okay.
Yeah, Dr. Subahan has something to do, so he left earlier.
Okay, great. No problem. Okay. And thank you, Dr. Lutfi. Maybe my pronunciation is not good. Sorry.
Shahab, yeah.
Shahab, okay. Thank you very much. Okay.
You're welcome. Yeah.
Okay. So thank you very much.
Yeah, you may leave the Zoom, I think.
Okay. Okay. Thank you. Bye bye.
Bye bye. Thank you. Ya, oke, terima kasih sudah menghadiri kuliah tamu hari ini. Semoga bermanfaat ya. Kurang lebihnya, kami mohon maaf. Wassalamualaikum warahmatullahi wabarakatuh. Ya, oke, saya tutup Zoom-nya ya.
Iya, Pak.